Okay, this is Chapter 6, Normal Probability Distribution, 6.1, the Standard Normal Distribution. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability. The first thing that we're going to look at is uniform distribution, which really doesn't happen very often, but it does make the problem of figuring out any of these very simplified. So we're going to go ahead and look at the graph of this. And so if you guys had the graph, a density curve, your random variable would be at the bottom and the probability would be on the vertical axis. And it says uniform probability, a continuous random variable has probabilities that are spread out evenly over the range, and this is going to make a rectangle. And rectangles are easy to deal with because we have the total area is equal to length times width. And each of these little rectangles would be equally width. Right below this, we do have an example that says the reaction time x in minutes of a certain chemical process follows a uniform probability distribution with x between 5 and 10. Draw a graph of the density curve. So I have the curve already sketched in here. Random variable x, which is time, it's continuous. And if you notice, it goes from 6 to 10. I'm just going to go ahead and make these all individual little rectangles here. And with that, each of those rectangles would have the same little area. And since the total area is 1 and we have 5 of these, each one would be making up 1/5. So if you could put 1/5 in all of those little rectangles, that would work. So see if you can put them in all of them. So the first problem here is that's our density curve. Part B says, what is the probability that the reaction time is between 6 and 8 minutes? So counting up those little blocks, we'd have 1/5 plus 1/5, which is 2/5. And again, you can express this as a decimal. I'm going to leave it as a fraction. C says, what is the probability that the reaction time is between 5 and 8 minutes? And again, counting those up, 1/5, 1/5, and 1/5 would be 3/5. And then what is the probability the reaction time is less than 6 minutes? Well, anything less than 6 minutes has a probability of 1/5 of happening. So again, uniform probability doesn't get used as often, but it does make the problems a lot nicer to be dealing with. So for most of us, the problems that we're going to be dealing with are going to use the normal distribution. So give that a big star. Normal distribution is if a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, and this total area under the curve is also equal to 1, just like it was for the uniform distribution. And with bell-shaped curves, what we've seen before, in the middle of the graph is our mean. I'm going to go ahead and use our population parameters here. And then we're going to go out 3 standard deviations each way. So 1, 2, 3, both directions. And so we're going to go ahead and have sigma, 2 sigma, and 3 sigma. And likewise, negative sigma, negative 2 sigma, and negative 3 sigma. So properties of a normal density curve says it is symmetric about the mean, 50% to the left of the mean, 50% to the right of the mean. Because the mean is equal to the median is equal to the mode. The curve has a single peak. It's the highest point occurs at the mean. The area under the curve is 1. The area under the curve to the right of mu is equal to 0.5, and same with to the left. As x gets larger and larger, the graph approaches, but it never touches the horizontal axes. The empirical rule holds true. We saw that in previous chapters. And the distribution of x using MyOpenMath, that needs a few stars there, is x has a little squiggly line, a tilde, in mu, comma, sigma. So if you have questions with MyOpenMath and it's going to have blanks in there, and it will say x tilde blank, and goes in if it's a normal, and then blank and blank, you're going to put in those blanks the mean and the standard deviation, which we are going to learn how to calculate in a minute. And then also, it's going to be sometimes given to you guys in the word problem. So definitely give that a star. So the next example that we have is the lives of refrigerators are normally distributed with a mean of 14 years and a standard deviation of 2.5 years. Draw a normal bell-shaped curve with the parameters labeled. So this is my normal bell-shaped curve. In the middle, I'm going to go ahead and put our mean, which is 14. And again, we're going to go out 3 standard deviations each way. So going out 1 standard deviation, I'm going to add 2.5 to our mean. So adding it, we're going to get 16.5. Subtracting it, I'm going to get 11.5. And then 2 standard deviations, so adding another 2.5, we get 19. And then subtracting another 2.5, we get 9. And then going 1 more standard deviation, adding another 2.5, we get 21.5. And then subtracting another one, we get 6.5. Shade the region that represents the proportion. And again, proportion here is the same thing as probability of refrigerators that last for more than 17 years. So more than 17, I'm going to go ahead and shade that in. And so 17 is going to be somewhere over here. And shading that, more than would mean longer than. So I'm going to shade to the right. I don't have any room down at the bottom to put 17, so I'm actually going to write the 17 up here at the top. The next thing says, suppose the area under the normal curve and to the right of 17 is 0.1151. Provide 2 interpretations of this result. So we can say, and you can write as a percent, so we can say 11.51% of fridges last more than 17 years. Another interpretation of it would be less than 17 years. And to figure out that area over here, since the total area is 1 minus the area that's to the right is 0.1151, we get that area to the left is going to be 0.8849. And so we can say 88.49% of fridges last less than 17 years.